Welcome to our video on plausible uncertainties for human post-regression. Computer vision models in the wild face various sources of uncertainty, such as domain shift, occlusions, and sensor noise. Beyond capturing a single measure of uncertainty, it can be beneficial to differentiate aleatoric and epistemic components. Aleatoric uncertainty comprises irreducible noise in the data generating process, while epistemic uncertainty indicates model immaturity and issues in model configuration. Numerous such methods exist and find application in human post-estimation. However, few if any assess whether their uncertainties are semantically or analytically plausible. Here, we compare two approaches for uncertainty estimation in HPE in terms of calibration and uncertainty residual correlation. In doing so, we introduce evidential deep learning to the HPE domain and derive multivariate deep evidential regression, highlighting subtle but important differences to prior work in multivariate evidential deep learning. We also motivate an additional recalibration step for the univariate approach and propose a set of explorations for the semantic plausibility of uncertainties in HPE. The first of our approaches combines maximum a posteriori estimation with variational inference. Here, we estimate the parameters of a Gaussian, but we resample the final layers of the model 50 times with intermittent dropout at inference time. The mean of the predicted means is the point estimate of a given joint coordinate. The mean of the predicted variance is the aleatoric component, and the variance of the predicted means is the epistemic component, comparable to disagreement of the submodels induced by variational dropout. Deep evidential regression requires no variational approximation. Instead, the predictive posterior from which we derive the negative log likelihood loss function is defined in terms of the parameters of the normal inverse gamma prior over the likelihood function. Uncertainty components follow directly from the moments of this prior. The same is true for the multivariate model, where instead of a variance, we estimate a covariance matrix, and therefore apply a normal inverse Richard prior. A simple example shows one major difference between the approaches. The jitter in the MAP model is a result of the stochastic sampling component. DER does not rely on sampling, which leads to a smooth function and increased performance in training and inference. Beyond visual inspection, we now analyze these estimated distributions in a principled way. First, calibration. A probabilistic regression model is considered to be calibrated if any given confidence interval contains the corresponding number of samples. If for a given model this is not the case, we can employ methods such as isotonic regression to adapt a learned quantile function and map the sample space adequately. A calibration plot can show how each model performs along this metric. A diagonal line indicates perfect calibration. In the univariate category, we find that the models are not well calibrated initially. In simple words, the majority of samples has a higher error than predicted by the estimated uncertainties, or the models are overconfident. On the other hand, both multivariate models are almost perfectly calibrated out of the box, with DER exhibiting a slight edge over MAP. Uncertainty residual correlation offers an additional perspective on the quality of our probabilistic model. Traditionally, higher correlation should indicate that one of the uncertainty components is better at capturing the expected error of the model. Here, DER and multivariate MAP are the clear winners in aleatoric and epistemic uncertainty respectively. Do note, however, that aleatoric and epistemic uncertainty should each make up only part of the true residual. Additionally, high epistemic uncertainty estimates should be fairly uncommon in the trained models we see here. Instead, epistemic uncertainty generally diminishes during the training process and only increases when the model is applied to a novel dataset with domain-specific variations. Departing from the analytical perspective, we now look at the semantic plausibility of estimated uncertainties. A common way of benchmarking aleatoric uncertainty estimates is introducing artificial, often Gaussian noise to the target values. In vision problems such as human post-estimation, this is often not easily achievable because labels are already corrupted by noise in the human or sensor-based labeling process. For this reason, we employ a simulated dataset with rig-based labels and add Gaussian noise of several magnitudes. Cumulative density functions of a DER model trained on this artificially corrupted label data indicate that the added noise is captured almost perfectly in the aleatoric component. The epistemic component does exhibit a slight increase in mean joint uncertainty, but the effect is much less pronounced, as we would expect. Lastly, we apply artificial occlusions to a familiar validation set and observe an increase in aleatoric uncertainty as the occluder size increases. This is semantically sound as a larger occluder effectively increases the plausible area for a given joint's position. Again, the epistemic component remains largely stable.